Good day everyone, welcome to my channel. For new here, please hit the like button and subscribe. Today, our topic is about KISSsys bevel gear design. I will show you the step-by-step process and standards used in this module, including fine sizing. Normally, the common design of bevel gear is that the axes of the two gears are perpendicular to each other. It's a 90 degrees angle, but in this tutorial we will design a bevel gear where the axes of the gears here are not perpendicular to each other as a requirement of the customer. Okay, let's start. So this tutorial will focus in bevel gear design. So one gear pair only in this model. So these are the data that can be generated in our bevel gear module in KISSsys software. So we can generate the 3D model, and this 3D model can be referenced for the CNC machining, like say you have a 5-axis machine. Then we can also generate the 2D drawings, and we can check the different simulation like transmission error, the stress here in our software. Okay, so in bevel gear classification we have 3 types of gear. We have these straight bevel gears. Of course, the shape of the teeth are in straight cut machining. And helical bevel gears, the shape of the teeth also is in helical form, while in spiral bevel gears, so the shape of course of the teeth is on spiral form also, but this is differentiated into 2 types. You have without offset. So in spiral bevel gears without offset, the axis is at the center of the gear and pinion, while in the with offset type, it's also called the hypoid gears, we have there an offset in the axis. So the offset leads to a bigger pinion diameter and therefore higher strength. Also, the overlap is higher and the gears are quieter. So these hypoid gears are commonly used in our gear differential. The disadvantages of these hypoid gears is that the offset creates horizontal sliding and therefore higher losses and higher risk of scuffing. Next, the bevel gear geometry in accordance with ISO 23509. So this data will be automatically generated in our KISSsoft software. So in strength calculation, the following standards are used for bevel and hypoid gear rating are implemented in KISSsoft. So we have different methods and standards used here, and these are all implemented in our software. Okay, next is the bevel cone types. We have different cone types in bevel design. The common cone types that we use in engineering university is this one, the standard ones. The root and apex are in 1 point. And also another one, we have this new standard. This was developed by Gleason. So the root, the apex is not in 1 point here. So later I will show you in our software. So this is the design requirements that we are going to design. Classification of the gear is straight bevel gear. So our customer has a constraint in machining. So that's why we develop only straight bevel gear with the power requirement of 2 horsepower and the input speed of 30 RPM with the gear ratio of 2.3, and the shaft angle is not perpendicular and is given 105 degrees, and the application is in agriculture and uniform light shock. I have added also here the ANSYS simulation for the ANSYS contact tool, which I will not show in this tutorial. Okay, So this software shows the contact tool of the 3D model generated from our KISSsoft model, shows excellent stress and contact point here. Okay, so let's start with our software. Okay, let's open our KISSsoft. Then next is move to routing module and select this bevel and hypoid gears, okay, cylindrical. Then given this data, we'll now input our requirements. So let's proceed to rating tabs. Then make sure you click this torque portion so that we can input the data in the power. So the given is in 2 horsepower. Again guys, we can change the unit by right clicking this portion. It could be kilowatts. Again, it depends on the given. Then let's proceed to the requirement speed. Let's say 30 RPM. And our application is agriculture. We will use 5,000 hours. So we have a reference here. It is arranged. Then for the application factor, so we'll use a light shock and uniform, so 1.25. Let's retain this data. Then for calculation method, we will select the latest, the 2014 method B1. Then let's keep the other data in default. The next is go back to basic data, and here we will update the shaft angle here. From 90, this is perpendicular to 105. Then again, let's retain all the materials. We use 18 chromium, nickel, molybdenum 7. The next step is we completed now the data inputting. We will proceed to sizing, gear sizing. For rough sizing, this one cannot be used because our data is spar gear. So the requirement for rough sizing, we need to input the data for spiral. So this is an error. Then let's proceed now to we run the data first, so that the inputted data will be bring to the KISSsoft memory. Then let's proceed now to find sizing. So here we will input our requirement. We have a ratio of 2.3. Then we will reduce the solution into 500. The next is normal module. We can select here, let's say, a range from 4 to, let's say, module 6. So in this tutorial, I will use step increment of 1 so that the software can simulate fast. Then normal pressure angle, we will retain the 20 degrees standard. When spiral angle, so this is straight, so we will select this as standard data. Then phase width of the gear, let's say 40 mm to 50 mm. Again guys, you can adjust the range. So for this tutorial, I will just use simple range so that the software can can simulate faster. Then of course, hypoid, this is not a hypoid, so just click. The number of teeth 11 to 24, set as default. Then click calculate. So the software, as you can see, will automatically compute the fine sizing, and the result is here, 72 solution found. So guys, next is what are the things that we need to check for the selection of the gear. So let's go to graphics. I will show you. So number 1, I will check always is the mass. The mass of the gear 1 and gear 2 should be, of course, lighter compared to the other one, but should pass the standard requirement. So for flank safety, our minimum requirement is 1.4 for standard, and for the root is 1.1. So here we can check with the road safety and the standard. So 1.4. Then we can check with the color blue. So this is lighter compared to others. So this one is acceptable, more than 1.4 and more than 2.25 with this weight. Okay, so we can zoom so that we can check what's the value. So we can select number 32 or number 30. Then let's go back to result. Then 32, find the condition number 32. Then let's check. Number 32, we have module 5. Okay. Then let's say the factor of safety for the root 1. So 1 point, let's go back. So factor of safety is 2.2, very high. For the gear 1, flank safety 1, 1.4. Then for the flank safety, 2.3. I think this is already acceptable, but guys, you can select any other gear with this weight. So the weight total here is 4 kilograms. Then you can accept. Then we need to simulate. So we can check here the road safety is 2.2, the flank is 1.4, so we have a very good factor of safety here. Then next we can check for the model. So graphics, geometry, 3D and run. So this is now our 3D model. Actually, I have already here a 3D model. So we can close this one, system. Then we can check the design. So view from the left. So right now we have this angle. So this is not perpendicular. The two axes are not perpendicular here, but we have a very good factor of safety. Then let's proceed now to contact analysis. So in contact analysis tab, we can automatically generate the coefficient of friction. This is between the two materials of the gear, so 0.1. Then for the axis alignment, this corresponds to the error of, let's say, for the bearing stiffness, for the gear, the shafting. So we have a movement for shafting. So, but if you don't know, for this tutorial, we can leave it at 0. But if you have data, we can check from shaft calculation. You can cancel here. Then it's okay for now for the axis alignment for this tutorial. Then let's calculate. So here we can check the transmission error. So let's just click OK. So we have negative 20 microns transmission error. Then other data, can get the torque here. So for simulation, let's go to graphics, contact analysis. Then we can see the contact pattern here. Let's say for gear 1. So this is the contact pattern. Transmission error for gear 1. Then other data like stress curve, 3D. We can have bending, stress, and root. So we can have in 2D. So this is the root. Okay. Then if you can decide that this is your gear, then you can download the 3D model. Just click this save as. Okay, another one, we need to put some data here in the shafting, like the hole diameter for the shaft. So from our computation with the horsepower using the PSMA code shafting 2 and 30. So for right sizing we have 44, so let's say 50 data. We can adjust that 3D model here at the basic data tab. Then you can go to details here, so to check for the diameter. Okay, then you can input, let's say 50, but for this inner diameter, I think the shaft is small. You can try to put 40, and let's try to run. So we can adjust to 50. So meaning our gear sizing, our shafting, rough sizing for shaft is okay. Then we can adjust the diameter. Just 50 on, okay. So this is now our reference. So you can save this as step model for the gear. Okay, you can simulate. Then if you have a 5-axis machine, you can use the 3D model as reference in the CNC programming. Just click this save, and you can save here a tutorial. So let's say step file Bevel here. So you can rename your own design Bevel gear, then just save. So the data now is saved as step file. Okay, then next you can close this one. So I think this is the end of our tutorial. So additional answers, this will be simulated in other form. Okay, thank you for watching, and God bless. Okay, bye bye.